Hi everybody, my name is Robert Brennan. I'm a PLL VCO applications engineer for Analog Devices based out of Boston. So in this presentation I'm going to show you how we can use frequency planning to greatly improve the performance of a PLL frequency synthesis system. So on the left here we have what we would ideally like is a straight, clean signal. But in reality, at a PLL or VCO output, we have a number of spurs or spurious signals and some phase noise, which is undesirable because they will result in system distortion and undesired mixing and modulation. Basically, you don't want them. So the main issue with high spurs is that if you have a frequency spectrum of, say, 1 gigahertz, if the spurs are too high at certain areas, you can't use output frequencies in those areas. So what we plan to do here is to move the spurs so that you can then reuse that spectrum that you previously couldn't use, and therefore you're getting better value for money. So just a simple introduction to a PLL VCO loop. On the right, we have a VCO which generates a output frequency. It's controlled by a tuning voltage that on the input. This tuning voltage is controlled by a PLL loop, which takes the feedback from the VCO, decides if it's too high or too low, and then tunes the VCO tuning voltage accordingly. The comparison of the feedback is done at a certain frequency. So in this case, we're looking at 100 megahertz. We have 100 megahertz coming in here and here to the PFD comparison block. The issue is that at integer multiples of that 100 megahertz, we have unwanted spurs. These are called integer boundary spurs. So at 1, 2, 3, 4, 5 times 100 megahertz, we have a spur, and we don't want that. So in this case, our divider is 20.01. So that means that our output frequency is 2001 megahertz, but because 2000 is a multiple of the PFD frequency, we're going to see a spur at a 1 megahertz offset. So this is showing a spur at a 1 megahertz offset. Here we have on the x-axis is your frequency offset from your carrier, and the y-axis is power. And we can see that 1 megahertz out, we have this large integer boundary spur, and that's going to be mixing with everything in our system, everything downstream from the PLL, and we don't want that. So what we do, I'm going to show you how to do, is how we can move that integer boundary spur, because if we move it to, say, a 10 megahertz offset, the spur gets filtered by the loop filter. The spur rolls off once it's outside the loop filter at 20 dB per decade. So if we compare the 1 megahertz and the 10 megahertz offset, we can see it's much lower and it's much less likely to be a problem here where it's less than 100 dBc. So how can we move this spur? How can we get it so that it's far out of the loop bandwidth and it's being filtered? So we can do it by changing the PFD frequency. But previously we were fixed at 100 megahertz, so the spurs happened at integer multiples of that. If we change the PFD frequency so that that integer multiple occurs far away from our target frequency, then the spur is no longer an issue. So to vary the PFD frequency, we have a couple of ways of doing it. I've zoomed in here on the PLL input. So one way we can change the reference input. So traditionally your reference would come from like a TCXO or crystal oscillator. But if you can get the reference from somewhere else that has a variable frequency, we can change that frequency and therefore change the PFD frequency and therefore change where the spur falls. The other way to do it is to change the OR divider. So the OR divider is an integer divider on the reference input. If, for example, we had, say, 80 megahertz at the reference input, we could use OR divider options of 1, 2, 3, and 4 to get 80, 60, 40, and 20. And we can then choose the optimum one that will put the spur as far away as possible. So we've built a piece of software to do this. I've described two options here for how we can vary the reference frequency. So on the top left, we're creating our reference frequency here, but it's coming out of a clock generation chip. So this clock generation chip it has a VCO running at a core frequency probably around 3 gigs or so. And then this clock is divided down and distributed to all the different parts of the system, so the PLL and the ADCs and DACs. And traditionally, people use a fixed divider on the output of the clock generation chip so that they get a fixed reference frequency. But you don't need to do that. So here we're saying, let's use the options of divide by 8, 10, 12, 14, and 16, and that gives me 5 different reference frequencies going into the PLL. The alternative way of doing it is to use a second PLL VCO loop to create the reference frequency. If you run that PLL VCO in integer mode, then you're not going to get any spurs from that, but you're going to get a bunch of available reference frequencies. So if here I've said, give me all reference frequencies between 250 and 350 megahertz. I haven't listed them here, but it's about 50. And all those options mean you've plenty of options to find an optimum PFD frequency. And then the best solution is to combine both techniques, where you get a large range of PFD frequencies, because the bigger that array of PFD frequencies, the more you can optimize the system. So this is the software we created. It's called ADI Sim Frequency Planner, which is quite a lengthy name. What we've done here is the user will come and they'll describe what system they want. So here I'm saying I want to start at 2000 megahertz, and every 1 megahertz I want an output frequency, and I'm going to do 1,000 steps, so up to 3 gigs. So what the software does is it will step through each of those output frequencies, and it will go through the array of available PFD frequencies and then choose the optimum one to give you that spur as far away as possible. So here's a flow chart of what the software does. First, the user specifies what they want. So this would be, say, the input to a mixer, what they want at that input, what frequencies they need. Then the software will look at all the available PFD frequencies, simulate the spur power. We've found that the simulation matches measurement very closely, surprisingly closely. It'll simulate first and second order integer boundary spurs. These tend to be the higher power spurs, the more problematic ones. And then it will choose the PFD frequency that gives you the furthest spur away, so the lowest power spur, while you can still get your output frequency. Then the software will return everything to you. There's a number of plots and there's a lookup table. And so the idea would be that you would export this lookup table into your system's firmware. So every time you need to set an output frequency, the firmware looks at the lookup table and sets the various dividers to get the desired output. So this is an example of the output settings. So in this case, my output frequency is 4.8 gigs. The software does its calculations. It says this is the optimum PFD frequency, and then to get that, set these dividers in a certain way. It also tells you the charge pump current to use, because when you change the PFD frequency, it plays with the loop filter dynamic, so you can mitigate that change by tweaking the charge pump current. But the software will take care of all of this, and it'll just present it to you in a lookup table, and then you can, the user doesn't need to do any work. So here's an example of the simulated I guess spur performance. So on the bottom I'm sweeping from 4.8 gigs to 6.3 gigs in 250k steps. So right here we're looking at, I think it's 6,000 channels. So each different channel, it's simulating the spur power. And we can see that in pretty much all cases, the spur power is less than 100 dBc. It's not problematic. And there's like one case or one or two small areas where there's still a problematic spur, but you've gone from, in the back, I'm not sure if you can see this, but the gray was the previous situation without any optimization, where about 10% of the channels you can't use, so you're losing 10% of your efficiency, whereas here we're down to much less than 1%. So this is the same plot on the right. I'm kind of zooming in, and what we can do, the software allows you to zoom in and look at a phase noise plot for each of these channels. So in this case, I've zoomed in on the worst channel here and basically turned it sideways, so I'm looking at the frequency offset, so it simulates the phase noise, and you can see your spur here at 10 kilohertz, and the power is shown. And then we can step through all the channels and see where these spurs occur and see how far they're being pushed outside the loop bandwidth, which is what we want. So here I've got, it's the same plot again, but this time I'm comparing it with our actually measured results. So the pink trace from the previous plot is now orange, and we can see it's simulating down at 120 dBc. When I actually measured this, I'm just measuring the noise floor of the spectrum analyzer. So it's pushed the spurs so far out from the target frequency that the spurs are extremely attenuated, which is exactly what we want. And we can see that where we did simulate a bad spur, the simulation matches measurement almost exactly. This is another example of the output charts that the software produces. So here it's the same frequency range, so from 4.8 gigs to 6.3. Again, we're doing 6,000 channels, and each channel it's showing me the optimum reference frequency and the optimum PFD frequencies. These are after the software has done its optimization and it said, right, so at 6 gigs you're going to use this PFD frequency and this reference frequency. It can be hard to read here, but it's also available in the lookup table output. And there's a bunch of other charts, I don't have time to go through them. So an example of how we implemented this to actually do it in the real world, I used one of our clock generator devices. So this is a low jitter clock generation and distribution chip where we have a core frequency running around 3 gigs, and then the part has 14 outputs that go to all different parts of the system. And in this case, I'm taking one of those outputs as the reference to the PLL. On the clock generation chip output, somewhere around here, we have the divider options, and that's where we're programming that value that the software has decided is the optimum value. And then on the right, I'm using one of our integrated PLL VCO parts. So this outputs 54 to 6800 megahertz, and that's taken its reference input from the clock generation chip output, and then it's using the reference divider to create this big array of PFD frequencies. And then from our lookup table again, we're going to program the reference divider and the end divider to get our actual desired output frequency. I think I'm out of time, sorry. That's the conclusion. Thank you. Sorry.
There's maybe some questions.
Yes.
Any questions? Okay, thank you.
Thanks.
This is a nice presentation.
Thank you. Thank you.